Hello my dear curious friend, and a very warm welcome to the Deepfield channel. Tonight we are going to wander through one of the most dizzying territories the human mind has ever dared to map. The possibility that the universe in which you breathe, dream and exist might be just one among countless others, and that somewhere beyond the reach of any telescope, a version of you is making decisions entirely different from the ones you made today. It is a subject I promise to approach with all the calm and gentleness it deserves, trying not to make it so fascinating that it keeps your eyes open until dawn. But before we dive into that shoreless ocean, I would love to hear in the comments which corner of the world you are listening from tonight, and if typing feels like too much effort, just leave a simple hello. It may seem small, but that tiny gesture tells YouTube that our space is a welcoming one and helps us bring more tired minds to unwind with us. If you enjoy our scientific journeys, please leave a like and subscribe to the channel. And for those of you who are already part of our community, thank you from the bottom of my heart. If you would like to grow even closer, consider becoming a channel member. Members receive early access to videos before anyone else, and the link for that is right here in the description. Now, wherever you are, find a truly comfortable position, release your shoulders, and let the weight of the day drift away. If sleep arrives during our conversation, accept its invitation without guilt. Let us begin. There is a question most people never speak aloud, yet one that rises quietly in those moments between waking and dreaming, when the mind loosens enough to allow the impossible. The question is this: what if I had chosen differently? What if that road not taken had led to an entirely other life, as real as this one, unfolding right now somewhere I cannot see or touch? For centuries, this was a question belonging to poets, to philosophers, and to people lying in the dark staring at the ceiling. Today, in a way that is both surprising and slightly unsettling, that question has migrated into physics laboratories, and scientists are not answering it with a condescending smile, they are answering it with equations. What quantum physics revealed over the past century is that reality, at its most fundamental level, does not work the way we imagine. It does not work like a well-lit room where every object sits in a defined place, with a clear history and a predictable path. It works more like a room wrapped in fog, where things exist in multiple overlapping states until the moment someone turns on the light and looks. And the part that physicists still debate with striking seriousness is what happens to all the other possibilities once the light comes on. Do they simply vanish? Or do they keep existing somewhere else, on some other branch of reality, completely unaware that here, in this room, you made a different choice? To understand why this question emerged from physics, and not merely from philosophy, we need to start at the very beginning. And the beginning, in this case, is almost disturbingly simple. Everything around you, this space where you rest now, the fabric touching your skin, the air flowing in and out of your lungs, the very architecture of your thoughts as these words reach your ears. All of it is made of atoms. You probably already know that, but what you may never have paused to truly feel is what it means to exist as an atom. An atom is almost entirely empty. If you took a hydrogen atom and expanded it to the size of a cathedral, the nucleus, the dense heart of that atom, would be roughly the size of a fly resting at the centre of the main nave, and the electron orbiting that nucleus would be circling somewhere near the outer walls of the cathedral, separated from the centre by a space that is, for all practical purposes, absolute emptiness. There is nothing between them. No substance, no ether, no filling, just space. This means that you, right now, are made of almost nothing. The solid matter you call your body, your bed, the floor beneath you, is overwhelmingly empty space held together by invisible forces. The sensation of solidity you experience when pressing your hand against a surface does not come from matter touching matter. It comes from electromagnetic forces repelling other electromagnetic forces. You have never truly touched anything in the strict sense of the word. Your hands came close enough for the forces between atoms to create a resistance that your brain interprets as contact. That alone would be enough for an entire night of contemplation. but it is only the entrance corridor of what we wish to explore, because atoms, no matter how small and hollow they are relatively large and comfortable structures when compared to what quantum physics actually studies. The territory of quantum mechanics is the territory of subatomic particles, electrons, quarks, photons of light, the entities that make up the atoms themselves. And it is in that territory that reality stops behaving like anything you have ever experienced. The first encounter with that territory usually comes through an experiment physicists affectionately call the strangest thing in the universe. Its formal name is the double-slit experiment, and it was first carried out in the early 19th century to study the nature of light, long before anyone suspected the implications it would eventually carry. The setup is simple. You have a source that emits particles. It could be light, it could be electrons, and you place in front of that source a barrier with two narrow slits open. On the other side of the barrier, there is a screen that records where the particles land. If you picture this with marbles, the outcome is obvious. You open two slits, shoot the marbles through, and on the other side of the barrier you see two clusters of marks, one for each slit. Each marble went through one slit or the other, left its mark, and that is that. Simple, predictable, intuitive. But when you run the same experiment with electrons, something entirely different happens. Instead of two clusters of marks, the screen on the other side displays a pattern of multiple alternating stripes, regions of many marks and regions of almost none, repeating like the ripples that form when two stones fall into water at the same time and their waves meet, reinforcing each other in some places and cancelling out in others. This pattern is called an interference pattern, and it can only arise if the electron passed through both slits simultaneously, like a wave that splits, travels both paths, and then interferes with itself on the far side. One electron, passing through two slits at the same time, interfering with itself. That alone would be disturbing enough, but physicists went further. They wanted to find out which slit the electron was actually going through, so they installed detectors to observe the electron at the moment it crossed the barrier. And here is what happened. The instant the measurement was made, the instant the electron was observed, the interference pattern vanished. The electron went through just one slit, like an ordinary marble, and on the other side appeared only two clusters of marks. The simple act of observing changed the outcome of the experiment. Read that sentence again, silently at your own pace. The act of observing changed the outcome. This is not poetry. It is not metaphor. It is not a philosophical trick of language. It is a documented experimental result, repeated thousands of times in laboratories around the world, with different types of particles, under different conditions, and always yielding the same unsettling outcome. Before being observed, the electron has no defined position. It exists in a superposition of possibilities, travelling multiple paths at once. Upon observation, that superposition collapses into a single reality. The technical term for that state of multiple simultaneous possibilities is quantum superposition, and the term for the collapse of those possibilities into one upon measurement is wave function collapse. These two concepts are the beating heart of everything we will explore in the hours ahead, because it is precisely here that the question of parallel worlds stops being fantasy and begins to become serious physics. Because think carefully, if the electron exists in superposition in multiple states at once, and if collapse happens only when an observation occurs, where do the other states go? When the wave function collapses and the electron appears passing through the left slit, what happens to the version of the electron that, an instant earlier, was passing through the right slit? Does it simply cease to exist? Or did it continue existing somewhere else, on some other branch of reality that took a different path from ours? This is not a rhetorical question. It is literally the starting point of one of the most serious and most debated interpretations of quantum mechanics, proposed in the mid-20th century by a physicist named Everett. But before we reach Everett and what he proposed, we need to understand more deeply what superposition means in the real world, because it is not limited to electrons in a laboratory. It applies in principle to everything that exists, including you. There is a famous thought experiment that helps make this idea visceral. almost physical, even though it exists only as a thought. It was proposed by an Austrian physicist named Erwin Schrödinger, and it involves a cat, a sealed box, a radioactive atom, and a mechanism that, if the atom decays, releases a poison. The radioactive atom is a quantum system, which means it exists in superposition, both decayed and not decayed at the same time, as long as it remains unobserved. If no one opens the box and looks, quantum mechanics says the atom remains in both states simultaneously. And if the atom is in both states, then the mechanism is in both states too, the poison as well, and therefore the cat inside the sealed box is, according to the equation, both alive and dead at once. Schrödinger proposed this paradox not because he believed cats could be alive and dead simultaneously. He proposed it because he wanted to expose the apparent absurdity of applying quantum rules to macroscopic objects. It was a critique, a challenge to the theory, but the theory survived. And the question Schrödinger's cat poses with such elegantly unsettling force is the same question posed by the electron and the double-slit. What happens to the alternative state when you open the box and the collapse occurs? For those who are beginning to feel the gentle weight of sleep arriving as these ideas settle into the mind like mist, that is precisely what this is, a soft doorway into something much larger. The question Schrödinger's cat leaves hanging in the air is not merely philosophical. It has a precise physical address, a point of origin in the timeline of science, a moment when a group of people gathered around an equation realized there was something living inside it that had not been invited but stubbornly kept appearing. To understand what happens to the alternative state when the box is opened, one must first understand where the energy comes from that keeps all these possible states existing simultaneously. And that energy is no metaphor. It has a name, a mathematical structure, and a consequence that completely transforms how one thinks about reality. Imagine you're in a completely dark room. There is no light, no movement, no sound. You might expect this room to be the perfect example of nothing, of absolute vacuum. But quantum physics says that even this room, even the most matter-deprived space imaginable, is never truly empty. Something is simmering there. Something that cannot be removed by any known physical process, something that exists not despite the absence of matter, but as a fundamental condition of space itself, that something has a name, quantum vacuum fluctuations. The quantum vacuum is not nothingness. It is more like a restless sea beneath a perfectly calm surface, where pairs of particles appear and vanish in fractions of time so small that no clock could ever capture them, yet whose effects are measured in laboratories with extraordinary precision. This phenomenon is governed by a principle that already lived inside calculations long before anyone fully grasped its implications, and which was articulated by a German physicist of precise gestures and penetrating gaze named Werner Heisenberg. Heisenberg was young when he formulated what became known as the uncertainty principle, and he did so not as a technological limitation, not as a flaw in measuring instruments, but as a constitutive property of nature. The principle states that it is impossible to know simultaneously, with absolute precision, both the position and the momentum of a particle. The more precisely you locate the particle in space, the less you know about its speed and direction, and the reverse is equally true. This uncertainty is not ignorance, it is ontology. The particle genuinely does not possess both values at the same time. There is a way to feel this principle before naming it. Think of a wave on the ocean. A wave has wavelength, frequency, energy, but a pure wave, perfectly defined in frequency, stretches across the entire surface of the sea without beginning or end, which means it is nowhere in particular. On the other hand, a localized disturbance, a precise point of agitation, is made up of the superposition of many different frequencies, which means it has no pure frequency. Localization and frequency mutually exclude each other in waves, and the quantum particle obeys the same logic because it is, in some profound sense, also a wave. This wave-like character of matter was not Heisenberg's assumption. It had arrived a few years earlier through the work of a French physicist named Louis de Broglie, who proposed, first as a hypothesis in his doctoral thesis, that if light could behave as a particle, then matter should be able to behave as a wave. The idea was met with skepticism and then confirmed experimentally. Electrons passing through crystals created diffraction patterns identical to those light produced when passing through slits, patterns that only exist because there is interference between waves. Matter literally interfered with itself. It was in this context of waves and uncertainties that Erwin Schrödinger, working separately and with a different approach from Heisenberg's, wrote an equation. Schrödinger's equation describes how the wave function of a quantum system evolves over time. The wave function, symbolized by the Greek letter phi, is not a wave of matter in space. It is a wave of probability, a wave that encodes all possible behaviors of a particle or system with amplitudes that indicate the relative probability of each possible outcome when a measurement is made. Schrödinger's equation is deterministic. Given the wave function at one instant, it predicts with exactness how that function will evolve at the next instant. There is no randomness in the evolution of the wave function. The randomness we observe in the outcomes of quantum experiments does not come from the equation itself. It comes from something that happens when we measure, when we interact with the quantum system, in a way that registers a clear and definite result. That moment is called the collapse of the wave function, and it is precisely here that physics becomes philosophy, and where the multiverse begins to emerge not as speculation, but as a mathematical consequence. Because Schrödinger's equation does not predict collapse, the equation does not say that the wave function collapses when measured. It simply keeps evolving, absorbing the measuring apparatus, the laboratory, the scientist, the surrounding air. Everything that interacts with the quantum system is taken in by the equation and continues propagating in superposition. Collapse was inserted into the theory from the outside as an additional rule, a pragmatic one, to make the calculations work and produce predictions that matched what experiments showed. But a young American physicist named Hugh Everett did not accept that additional rule. He felt it was a scar on the theory, a patch that concealed something deeper. In the mid-20th century, as part of his doctoral thesis at Princeton University, Everett proposed something radical. What if Schrödinger's equation were simply correct all the time, without exception, without collapse, without any extra rule? What if superposition never collapsed but simply kept expanding to include everything, including the observer? What would the equation say in that case? It would say that when an electron in superposition is measured, the result is not that a single state is chosen and the others disappear. The result is that the observer enters superposition with the electron. There exists a version of the observer who saw the electron on the left, and there exists another version of the observer who saw the electron on the right. Both are equally real, equally present in the total wave function of the universe. The world branches, and each branch contains a complete and consistent version of reality. Everett called this the relative state formulation. His colleagues later called it the many worlds interpretation. His advisor, John Wheeler, was fascinated and disturbed at the same time. Niels Bohr, who had developed the prevailing interpretation of quantum mechanics in Copenhagen, met with Everett and left the meeting unconvinced. The idea was ignored for decades, partially published, partially shelved. Everett left physics and went to work in military strategic analysis. He died relatively young, without ever seeing his idea taken seriously by the scientific community. But the idea survived because the mathematics survived, and the mathematics was impeccable. What Everett had done was not speculate about parallel worlds for aesthetic or philosophical reasons. He had shown that if you take Schrödinger's equation seriously, if you do not insert collapse as an additional rule, then many worlds are an unavoidable consequence. You do not choose to believe in many worlds. You choose not to believe in the equation. This is the energy source of the quantum multiverse. It is not an external force creating worlds from nothing. It is the very evolution of the wave function, deterministic and uninterrupted, generating branches with every interaction. The universe does not explode into copies. It differentiates internally, like a river encountering an island and flowing through two channels that never meet again. Energy is neither created nor destroyed. The total wave function conserves everything. What changes is the distribution of correlations within it. There is a fundamental imbalance at the heart of this process, and it has a technical name that physicists took decades to articulate with precision: decoherence. When a quantum system in superposition interacts with its environment, the different branches of the superposition stop interfering with each other. It is as if the two channels of the river grew walls so thick that the waters of one could never again influence those of the other. Each branch becomes, from a practical standpoint, a separate world, with its own consistent history, its own classical objects, its own macroscopic laws emerging from the underlying quantum substrate. Decoherence is not collapse. It is something subtler and more real. Collapse was a magical intervention, a moment when the equation stopped applying. Decoherence is a physical process, measurable, calculable, one that explains why we, inhabitants of macroscopic worlds, do not perceive superposition around us. Every molecule of air that touches an electron, every photon that bounces off an object, every microscopic interaction carries information into the environment and effectively separates the branches of the wave function with a speed that makes coherence between them practically impossible to restore. The timescale on which this happens is staggering. For an object the size of a large molecule, decoherence occurs in minuscule fractions of a second. For an object the size of a virus, even faster. For an object the size of a speck of dust, practically instantaneous. For a human being, decoherence occurs on timescales so short that the concept of macroscopic superposition becomes operationally invisible, even though it remains mathematically present. This is where physics returns to everyday life in a way that makes the head spin gently. Every decision you make, every moment when two possible futures open before you, Everett's quantum mechanics does not say you choose one and the other disappears. It says both continue, that the universe forks and each branch contains a version of you living out the consequences of each path, not as metaphor, not as poetry, as the direct application of a differential equation that has never failed in any experiment where it has been tested. And if every quantum interaction, every collision of particles, every photon absorbed by every atom throughout the entire history of the cosmos has generated its own branching, and if this happens in quantities that no human language has adequate words to describe, then what do you get when you add it all up across billions of years of an expanding universe, with every star, every planet, every grain of sand, every carbon atom inside every cell of every living being that has ever existed participating in the same ceaseless process of branching? The answer is a structure, not the chaos one would expect from such a wild and relentless process, but something physicists have been compelled to acknowledge with a kind of involuntary awe. The branches of Everett's multiverse do not distribute themselves randomly. They organize themselves, and the discovery of how they organize has led physics to a place few expected to find when it all began with an equation written on a blackboard at an American university in the mid-20th century. The physicist Wojciech Zurek was among the first to realize that decoherence by itself does not fully explain why we live in a world that looks classical. Decoherence scrambles quantum interferences. Yes, it makes branches practically invisible to one another, but it does not, on its own, explain why certain configurations of the world survive the process of entanglement with the environment, while others dissolve without a trace. There is a selection principle at work within the branching structure, and Zurek spent decades refining the language needed to describe it. He called this principle quantum Darwinism, and the choice of name was not accidental. Quantum Darwinism starts from an observation that seems simple but conceals considerable depth. When you observe something around you, when you see a chair across a room, you're not receiving information directly from the object. You're receiving copies of information that the object imprinted on the environment around it. The photons of light that struck the chair scattered in all directions, made contact with the air, the walls, the floor, and reached your eyes carrying a fragment of the object's quantum signature. The environment acts as a communication channel, and the chair exists as a perceivable classical object precisely because it was able to imprint redundant copies of its information onto countless fragments of the environment simultaneously. The quantum configurations that survive selection are not the strongest in any usual sense of the word. They are the most redundant. They are the ones capable of recording their information in more fragments of the environment at the same time. A delicate superposition between two states rarely manages to do this, because the two terms of the superposition tend to produce interference patterns in the environment that cancel each other out before propagating far enough to reach an observer. A well-defined classical state, on the other hand, propagates copies of itself into so many fragments of the environment that the information becomes, in practice, impossible to destroy through any local interaction. The result is that the observable universe is not a democratic one. Within the vastness of branches that quantum mechanics generates at every instant, only a small fraction possesses the property of being observable from multiple and consistent perspectives. It is those branches we call classical reality. The others exist mathematically with equal validity, but they cannot propagate as accessible information through the environment. They exist in silence, without observers who know them as such, inhabited by versions of the cosmos that never needed to learn how to appear classical, because they never had the opportunity to record their history in the fabric of the environment around them. This creates a geometry of branching that is neither flat nor random, it is hierarchical. The most robust branches, those corresponding to histories with high information redundancy, subdivide into child branches that inherit the solidity of their parents. The histories in which matter organized itself into structures capable of propagating information efficiently, where planets formed stable surfaces, where complex molecules maintained reproducible configurations, where nervous systems developed the ability to integrate environmental copies into coherent models of the world. Those histories generate conditions for even more copies of information to propagate, which further favours the classical solidity of subsequent branches. There is a British physicist named David Deutsch who looked at this structure and saw something others had overlooked. Deutsch was one of the architects of quantum computing theory, and his mind was trained to think in terms of information flow between branches. He realised that the branching structure of Everett's multiverse is not merely an uncomfortable consequence of quantum mechanics. It is the mechanism by which information exists robustly anywhere. The classical reality we perceive is not what remains after the multiverse discards the improbable branches. It is what emerges when histories with a high degree of information redundancy overlap consistently from the perspective of multiple observers. Deutsch went further and proposed something that sounded controversial when first formulated, that the branches of the multiverse are not merely abstract mathematical structures, but that they have physically verifiable consequences. Quantum interference, that phenomenon in which electrons pass through two slits simultaneously and produce patterns that only make sense if the electron interacted with itself, is, for Deutsch, the most direct evidence that the other branches exist. The electron in one branch interferes with the electron in another branch. Interference is not a mathematical abstraction. It is a physical signal that crosses the boundary between branches before decoherence separates them irreversibly. The distribution of branches across cosmic time has a geometry that physicists are still learning to map. In the early universe, when all matter and energy were confined to immeasurably small volumes, and the temperature was so high that quantum interactions occurred with an unimaginable density, the rate of branching was of an intensity that has no parallel in any subsequent era. Every collision between primordial particles generated new branches, and those branches subdivided again before the previous ones had even had time to stabilize. The cosmos was born not as a single point expanding into empty space, but as a forest of possible histories separating from one another at a speed that human language lacks the grammatical structure to describe with precision. As the universe expanded and cooled, the density of interactions dropped. Particles became less frequent per volume, temperatures fell enough for stable structures to form, and the rate of branching, though it never stopped, changed in character. Branching became increasingly shaped by gravity, that force which operates on enormous scales, and which quantum mechanics has not yet fully incorporated into its formalism. Gravitation caused certain regions of the cosmos to condense matter into clouds, then into stars, then into galaxies, creating conditions for specific types of quantum interaction, those occurring inside stars, on the surfaces of planets, in atmospheres rich in heavy elements forged by generations of stellar explosions, to become the dominant generators of new branching in the histories that resemble ours. The American physicist Hugh Everett, the original creator of the many worlds interpretation, never lived to see the full development of the ideas his doctoral thesis set in motion. He wrote his proposal in the mid-20th century, was met with a combination of skepticism and misunderstanding that deeply discouraged him, and withdrew from academic physics before the conceptual instruments necessary to appreciate the depth of what he had proposed had been developed. Decoherence as a precise quantitative mechanism was formalized decades after his death. Zurich's quantum Darwinism came even later. The connection between branching and information redundancy that Deutsch explored belongs to the late 20th century and the beginning of this one. Everett threw a stone into a pond and walked away before seeing the ripples form. The ripples, however, continued, and they revealed that the large-scale organization of Everett's multiverse possesses a property physicists call historical consistency. For a set of branches to form a history that appears classical to its inhabitants, the events within that branch must obey a precise mathematical condition. The records of past events, the marks events leave on the surrounding matter, the memories stored in physical systems, must be mutually consistent. There cannot be, within a single robust branch, a stone that remembers falling, and simultaneously a floor that does not remember receiving it. Historical consistency is the criterion that separates habitable branches from branches that exist mathematically, but could never contain observers capable of telling their own story. Murray Gell-Mann and James Hartley, working together from perspectives slightly different from those of Everett and Deutsch, developed what they called the consistent histories or decoherent histories formalism. Gell-Mann, who had received the Nobel Prize for his work on quarks, and Hartle, a cosmologist specializing in the quantum mechanics of the universe as a whole, realized that the correct question was not which branches exist, but which sets of branches can be described as coherent histories from the perspective of any internal observer. The answer was that the set of coherent histories is immense, but it is an infinitesimal fraction of the set of all mathematically possible branches. This has a consequence that connects with a far broader question. Why does the universe appear to have laws? Why do the same equations that describe the fall of an apple in Newton's garden also describe the orbit of planets around distant stars and the behavior of particles in an accelerator's deep underground? If the multiverse contains all mathematically possible branches, and if most of those branches lack the property of historical consistency, then the branches that do possess that property, precisely the habitable branches, are those in which the behavior of matter is describable by regular, repeatable laws. The appearance of lawfulness in the universe, the fact that there is something called a law of physics, may be a consequence of the selection of consistent branches within a deeper structure that possesses in itself nothing resembling a law. It is like asking why every river seems to follow a coherent path from source to sea, when the answer is that we call a river only the flow of water that found a continuous course. The flows that found no path never reached the sea. They did not form rivers. They continued existing as scattered moisture in the earth, invisible as global stories, present only as local conditions that never articulated themselves into a narrative of beginning, middle, and destination. The patterns that emerge from the large-scale organization of the multiverse therefore reveal a layered structure. At the deepest layer, the process of ceaseless, directionless branching At the intermediate layer, the Darwinian selection of states with high information redundancy. At the outermost layer, the one we inhabit and call the world, the histories that survived long enough and with enough consistency to contain observers capable of noticing they are inside a story. Each layer emerges from the previous one without having been planned by any of them. Order was not imposed. It grew the way complex patterns grow in systems no one designed to produce them. This layered structure is not merely an abstract description of how the universe organizes itself. It has consequences that reach all the way here, to this moment, to the temperature of the air you're breathing now and the cadence of your eyelids growing heavier as the night deepens. To understand how the multiverse leaves its mark on the visible world, we need to speak of an amplifier, a mechanism physics knows well, one that appears in modest and seemingly trivial places, but which holds within itself the capacity to transform the indistinguishable into the distinct, the possible into the real, the quantum whisper into something you can touch with your fingertips. This amplifier has a name that sounds almost bureaucratic for something so extraordinary. Physicists call it decoherence. The word comes from Latin and carries the idea of something losing its coherence, its ability to keep different parts synchronized. But calling decoherence merely a loss would be like calling the birth of a child merely a separation of cells. What decoherence does is not destroy, it reveals. It is the mechanism by which the quantum world, with all its superposition and interference and ambiguity, gradually transforms into the classical world you know, the one with defined objects, single histories, measurable consequences. To understand why decoherence is so powerful despite seeming so quiet, one must comprehend what it amplifies. In the quantum world, particles maintain between them a relationship called entanglement and a property called phase coherence. When two quantum objects are coherent with each other, they behave like waves arriving at the same point in synchrony, capable of interfering constructively or destructively, of adding together or cancelling out. That interference is the heart of quantum mechanics. It is what distinguishes an electron passing through two slits from a tennis ball passing through two windows. The ball goes through one or the other. The electron goes through both at the same time, and the proof of this is that the two trajectories interfere with each other and produce a pattern that could not exist if only one trajectory had occurred. Decoherence is the process by which that state of interference dilutes, and it dilutes because the environment is insatiable. Every particle in the real world is constantly interacting with neighbours, with ambient light photons, with air molecules, with weak magnetic fields, with the surrounding temperature. Each of these interactions is a kind of measurement, not a measurement made by a laboratory with sophisticated equipment, but a measurement in the most fundamental quantum sense. An event in which information about the system's state leaks into the environment and spreads across an ever-growing number of degrees of freedom. When that information is spread through enough photons, through enough molecules, through enough interactions, it becomes effectively unrecoverable from the perspective of any local observer, and when information becomes unrecoverable, interference vanishes. The branches describing different possibilities lose the ability to add together or cancel each other out. They become, in the technical language of physics, orthogonal to one another. This means each branch moves in a direction of state space that has no overlap with the direction of any other branch. They continue existing in Everett's interpretation, but they become mutually invisible. One branch cannot be accessed, influenced, or even detected by any measurement made within another branch. They have become separate worlds, not by a physical boundary, not by a wall or a distance, but by a structural difference in the way quantum states organize themselves in mathematical space. What makes decoherence such an extraordinary amplifier is the speed at which it operates. For large objects, the timescale needed for decoherence to complete is absurdly small. An object the size of a speck of dust in contact with air at room temperature loses its quantum coherence in a time that would need to be written as a decimal point followed by more than 16 zeros before the first significant digit. That is a fraction of a second so small that no clock in the world could register it directly. For a large molecule in solution, the time is comparable. For a grain of salt, for a living cell, for any object you can see with the naked eye, decoherence happens so quickly that for all practical purposes it is instantaneous. This explains why you have never seen a chair in superposition. Not because chairs are made of a different material from electrons, not because there is a special law forbidding large objects from exhibiting quantum behavior, but because the environment amplifies any deviation from classicality so swiftly and so completely that no conceivable experiment could capture the superposition state before it dissolved. The chair exists in only one place, not because quantum physics does not apply to it, but because decoherence acted on it long before any eye or instrument had a chance to look. This mechanism has visible manifestations, and some of them you can notice even without any equipment. The first and most everyday is the very sharpness of the world, the fact that objects have defined edges, that an apple ends here and the air begins there, that your hand is distinct from the table it touches. All of this is a manifestation of decoherence operating at every instant. At the quantum level, the distinction between the apple and the surrounding air is a matter of quantum state difference, that the environment reads and records ceaselessly. The sharpness you see is the accumulated result of trillions of imperceptible measurements happening every fraction of a second. The second manifestation is the direction of time. Quantum mechanics in its most fundamental form is reversible. The equations describing the evolution of a quantum system work equally well forward and backward in time. There is nothing in Schrödinger's equation that distinguishes past from future, and yet you live in a world where the past is fixed and the future is open, where a broken glass does not spontaneously reassemble, where memories point backward and expectations point forward. This asymmetry, this sense of time that seems so obvious and inevitable, emerges largely from decoherence. When information leaks from the system into the environment irreversibly, it creates an asymmetry. The past state of the system has been recorded in the environment. The future state has not yet been. This is what gives time its subjective direction, its feeling of unidirectional flow. The third manifestation is more subtle, and at the same time more intimate. It is the experience of making a decision. When you faced a choice a few hours ago, a few weeks ago, a few years ago, there was a moment when the future seemed genuinely open, when the weight of possibilities was palpable, when something had not yet closed. Then the choice was made, and what had been possible became past, and what had been another path became a path not taken. That process, seen through the lens of Everett's Multiverse, is literally the process of decoherence acting on the quantum state of the system that you are. In the instance before the choice, the branches corresponding to different decisions were still close enough that interference between them was in principle possible. After the information about your decision spread through the environment, through the sound of the words you spoke, through the position your body assumed, through the synapses that fired and left traces in neural networks, the branches became orthogonal, irreversible. The path not taken continued existing, but it continued existing in another branch, invisible from here. The physicists who studied decoherence over the decades following Hugh Everett's work identified several distinct regimes in which it operates in slightly different ways. These regimes received names that reflect the conditions under which they occur. One speaks of environmental decoherence when the primary agent is the thermal bath of particles surrounding the system, the constant background noise of temperature. One speaks of measurement decoherence when an experimental apparatus deliberately interacts with the system and scatters its information throughout the laboratory's records. One speaks of spontaneous decoherence in theoretical models where space-time itself possesses a granularity that forces the separation of branches even in the absence of any external environment, an idea that appeared in the work of researchers like Roger Penrose, who proposed that gravity could be the fundamental mechanism by which superpositions resolve into definite states, not through the environment, but through the geometry of curved space. This idea remains controversial and awaits experimental verification, but it illustrates something important about how the scientific community has come to think about decoherence, not as an accidental secondary effect, but as a mechanism with variations, with regimes, with its own boundaries that need to be mapped and understood. It is not merely the background noise of the world, it is the border between worlds. Inviting you to notice these manifestations in your own experience is not a metaphor. It is a physical observation. Look at the nearest surface to you right now, the sharpness it has, the fact that you can tell where it begins and where the space around it ends, is the product of an incalculable number of quantum interactions that have occurred and continue occurring at every instant, spreading information, closing branches, making the world you inhabit more classical each time you observe it. You're not merely a spectator of the decoherence process, you are one of its agents. Every time you interact with any object, you contribute to the spilling of information that separates branches and makes the past immutable. You are at every conscious moment participating in the construction of classicality, and now the system seems stable. The world around you, in this moment of calm and night, appears in equilibrium. Objects are where they are. The laws governing them apply with consistency. The branches that separated have remained separated, but stability comes at a price, and that price is the existence of conditions under which it can be lost. Quantum physics does not treat stability as a natural and permanent state of the universe. It treats it as a state earned, actively maintained by processes that consume time, energy, and relationships. Where those processes weaken, where the conditions that sustain the classicality of the everyday world are removed or disturbed, something different emerges. Not the random chaos the word disturbance usually evokes, but something far more precise and far stranger. The emergence of regimes in which quantum behavior is not confined to the scale of subatomic particles, but manifests in domains that defy the intuition of anyone who grew up in a world of solid objects and predictable trajectories. To understand how this happens, one must speak of threshold. The word has appeared before in the language of quantum physics, always carrying the same unsettling promise. On the other side of a boundary, the rules change. In the structure we have built over the previous parts, the relevant threshold is the point at which the decoherence rate, that speed at which a quantum system loses coherence by becoming entangled with its environment, drops below a critical value. As long as it remains high, branches separate quickly enough for the classical world to stay intact, but when it decreases, when a system is sufficiently isolated, sufficiently cold, sufficiently small, the separation between branches ceases to be instantaneous and begins to be gradual. And in that gradualness, something extraordinary becomes possible. The system begins to behave as if it were still in more than one state at the same time. This is not philosophy. It is what happens in laboratories around the planet, in experiments that take years to prepare and that occur at temperatures a minuscule fraction above absolute zero. The point at which thermal motion, that great promoter of decoherence, is reduced to the minimum physically allowed. Under these extreme conditions, electrical circuits the size of a coin exhibit behaviors that only made sense for individual electrons. Two opposite states of electric current coexist in the same structure at the same time, not as an imprecision of measurement, not as a limitation of the instrument, but as a verified and repeated physical reality. The threshold has been crossed. The system has left the classical regime and entered what physics calls the regime of macroscopic quantum coherence. And when one speaks of macroscopic in this context, one does not mean merely size, one means complexity. One means a system composed of an astronomical number of particles, all moving together, all participating in a single quantum state that encompasses them without exception. The word physics uses to describe this condition is collective superposition, and it represents one of the most dramatic phenomena the quantum universe produces when its usual constraints are lifted. Collective superposition is not a laboratory curiosity. It has a cosmological role that physicists took decades to begin to understand. In the early universe, in the first instance after what we call the Great Beginning, conditions of temperature and density were so extreme that the distinction between the quantum regime and the classical regime simply did not exist. Everything was superposition. Everything was coherence. The branches we know, the worlds we inhabit, had not yet separated with the firmness they have today, and the quantum fluctuations that existed in that primordial state, those small oscillations in the fabric of reality that quantum mechanics permits and even demands, were amplified by the accelerated expansion of the universe until they became the seeds of galaxies, clusters, and the large-scale structures the cosmos displays today. This means that the map of the night sky, that distribution of stars and galaxies that generations of astronomers have catalogued with patience and wonder, is an enlarged photograph of quantum fluctuations that occurred in a fraction of a second after the birth of the universe. The dramatic emerged from the microscopic. The visible cosmos is a consequence of a threshold crossed in the most distant past that exists. But let us return to the present, because the present has its own thresholds, its own breaking points, and they happen with a frequency that no calm night can fully erase. In certain nuclear processes, quantum behavior does not merely persist under special laboratory conditions. It governs phenomena that occur continuously inside stars, in reactors, in radioactive substances that exist in minute quantities in nearly every natural environment. Radioactive decay is, in its essence, a phenomenon of quantum instability. An atomic nucleus exists in a state that quantum mechanics describes as a superposition between two regimes, the regime in which it remains intact and the regime in which it fragments, releasing energy and particles. There is no classical cause that determines when the decay will occur. There is no observable external trigger, no accumulated pressure, no measurable stress preceding the event. The nucleus simply crosses the threshold at a moment that physics can only describe probabilistically. And when it crosses, a branch of Everett's multiverse separates from the rest. In one branch, the nucleus decayed. In another, it remains intact. The separation is real, it is physical, it is governed by the same equations that describe everything else, and it occurs in every radioactive atom in the universe, at every moment, without stopping. The dramatic is not a special state reserved for extraordinary moments. It is the ceaseless background against which the apparent stability of the everyday world is woven. While you rest, somewhere inside the sun that will warm this hemisphere tomorrow, protons are crossing barriers that classical physics would declare impassable. Quantum tunneling, that process by which a particle crosses an energy barrier without ever having had enough energy to overcome it by Newtonian logic, is the mechanism that sustains stellar nuclear fusion. Without it, stars would not exist with the longevity they have. The energy that made life possible on this planet depends on a phenomenon that only makes sense in quantum grammar, and that phenomenon occurs trillions of times per second while the night passes over you. Tunneling is, by its very nature, an example of a threshold crossed in dramatic mode. The particle does not climb over the energy barrier. It passes through it from within, from one side to the other, without ever having been in the forbidden space between the two sides. In terms of multiverse branches, this means that in countless versions of reality, the particle did not cross. In another version, it did, and it is in that version that a chain of events began, one that led to a burning star, that led to a planet with liquid water, that led to a long journey of billions of years of chemistry and evolution, that led all the way to this moment in which you breathe and your consciousness moves through these words. Humanity has learned to observe these phenomena with instruments of increasing sophistication. Gravitational wave detectors, installed at strategic points on the planet, monitor distortions in space-time with a precision equivalent to measuring the distance between Earth and the nearest star with the accuracy of a single human hair. They do not detect the multiverse directly, but they detect events so energetic, black hole collisions, neutron star mergers, that they represent the most intense regime of gravitational behavior physics knows, And in each of those collisions, physicists hope to find signatures that help distinguish between different proposals for how the universe behaves in its most extreme regimes, where gravity and quantum mechanics would need to coexist in a language that has not yet been fully written. Quantum interferometry experiments, on the other hand, work at the opposite scale. Instead of detecting cosmological events at distances of billions of light years, they manipulate individual quantum systems with such precise control that it is possible to observe the exact moment a system enters and exits the coherence regime. These experiments map the boundary between worlds with a resolution that would have seemed impossible to the generation of physicists who formulated the first principles of quantum mechanics. They show that the threshold is not a rigid line, it is a region with thickness, with texture, with its own behaviour that depends on temperature, pressure, the composition of the system and the surrounding environment. The structures that persist when a quantum system is held in the dramatic regime long enough have properties that engineers have learned to exploit. Quantum computers, for example, are not merely faster versions of conventional computers. They are machines that deliberately operate on the boundary between branches, maintaining superposition states long enough for computations to occur across multiple possibilities simultaneously, before decoherence collapses the result into a single classical value. Each operation of a quantum computer is, in miniature, a controlled incursion into the territory that Everett's interpretation describes as the internal structure of the multiverse. The attempt to build these machines revealed something no theory had predicted with sufficient clarity. Decoherence is not uniform, it has spatial structure. Certain regions of a quantum processor lose coherence faster than others. Certain configurations of atoms are more resistant to environmental noise than others. Learning to map this heterogeneity to find the most stable points within a chaotic field has become one of the most demanding disciplines of modern engineering. And in doing so, engineers began to wonder involuntarily whether they were charting a property of matter or a property of the space between worlds. That question has no answer yet, but the fact that it can be asked with mathematical rigour and not merely with speculative poetry represents a profound transformation in the relationship between theoretical physics and the built world. For decades, the multiverse was treated as an interpretive luxury, an elegant way to avoid the paradox without adding anything observable to the menu of science. What quantum engineering has begun to suggest is different, that the structure of the space of possibilities has real texture, and that this texture can be touched, measured, and even manipulated by those who know where to press. The primary partner with which the quantum system exchanges energy is not an obvious neighbour. It is not heat, although heat matters. It is not light, although light also enters the equation. The fundamental partner of any quantum system is the vacuum. The quantum vacuum, contrary to what its name suggests, is not empty. It pulses. It seethes with fluctuations that emerge and disappear on timescales so small that no instrument can track the individual motion of each event directly, only their cumulative effects on the surrounding matter. Every atom in your body is immersed in this invisible ocean, in permanent contact with a reservoir of energy that is not still for even a fraction of an instant. This exchange of energy between the quantum system and the vacuum is responsible for phenomena that classical physics could not explain. The Lamb shift, discovered in the mid-20th century, showed that the energy levels of the hydrogen atom were slightly different from what theory predicted, precisely because the electron is not only interacting with the nucleus, but with the constant noise of the vacuum around it. The Casimir effect, in turn, demonstrated that two metal plates positioned at very small distances from each other are pushed toward one another by forces arising from vacuum fluctuations excluded from the space between them. These two effects, separated by decades of investigation and measured with increasing precision over generations of experiments, point to the same foundation. The universe has no true state of rest. When one thinks of the multiverse from this angle, something shifts in perception. The constant branching described by Everett is not an extraordinary event that happens from time to time, when an electron is measured in a laboratory. It is the basal heartbeat of the real. The vacuum that pulses, the fluctuations that emerge and vanish, the superpositions that entangle and disentangle at every point of space and time. All of this is the continuous breathing of a structure that is always unfolding into versions of itself. The laboratory measurement that so fascinated the founders of quantum mechanics is just a particular case, a moment when the process becomes sufficiently visible for instruments created by conscious beings to record it. In the short term, what one observes of this dynamic is the apparent solidity of the classical world. Objects fall, temperature equalizes, waves propagate and dissipate. Decoherence acts so rapidly on human-scale objects that the underlying quantum behavior becomes imperceptible within infinitesimal fractions of a second. Decades of measurements, of experiments repeated under controlled conditions, have confirmed that the classical regime is not an illusion, but a robust emergence of quantum principles operating at an amplified scale. What changes in the short term is the internal state of microscopic systems, the spins of electrons in crystals, the coherence of photons in optical fibers, the phase of ultra-cold atoms held near absolute zero. These are the components of the picture, but the picture itself appears stable. In the long term, the story is different. On scales of centuries, the accumulation of irreversible quantum processes begins to leave marks that classical physics cannot trace back to their origin. Biological evolution, for example, depends on mutations, and there is growing evidence that certain mutations originate in genuinely quantum processes, such as proton tunneling within DNA molecules during replication. If this is confirmed with the solidity that preliminary data suggest, then the tree of life as we know it is, in part the result of quantum bifurcations accumulated over billions of years. Every existing species would be the expression of a set of tunneling events that occurred this way and not another, while other possibilities were realized in other branches of the state space that Everett's interpretation describes. On scales of millions of years, sensitivity to initial conditions becomes overwhelming. The universe is a system with so many degrees of freedom interacting in so many ways that any microscopic perturbation, any vacuum fluctuation at any point in space, has the potential to propagate, amplify, and translate into macroscopic consequences given enough time. The extinction of species, the formation of solar systems, the trajectory of comets crossing planetary orbits, all these phenomena carry, buried in their causes, influences that trace back to individual quantum events, magnified by cascades of interactions. Not in the sense that each quantum event determines the fate of a star, but in the sense that the universe's space of possibilities is so vast and so sensitive that the distinction between what is determined and what is contingent loses sharpness when looking at very distant horizons. This sensitivity to initial conditions is the fundamental limit of human prediction. It is not a technological limit that will be overcome when computers become faster or instruments become more precise. It is a limit inscribed in the structure of reality. Quantum mechanics is not merely strange in its details, it is strange in its architecture, and that architecture implies that the universe contains at every instant more possibilities than any mapping could capture. Prediction, then, is not revealing what will happen, but computing probability distributions over spaces of possibility that are, in principle, richer than any finite representation can contain. There is something profoundly human in the reaction to this discovery. When classical physics described a deterministic universe, the discomfort was philosophical in nature, a sense that freedom was illusory, that the future was already written. When quantum physics introduced genuine randomness, the discomfort changed shape but did not disappear. Now it seemed the universe was arbitrary, that there was no deep structure, only random draws. Everett's interpretation proposes something different from both extremes. The universe is not deterministic in the classical sense, because the branches that form are all equally real, but it is not arbitrary either. because the distribution of probabilities among the branches follows patterns that Schrödinger's equation describes with absolute precision. What emerges from this picture is a kind of beauty that does not resemble the beauty classical physicists celebrated. Classical beauty was that of a perfect clock in which every gear meshed with the next out of absolute necessity. Quantum beauty is different. It is the beauty of a system that is simultaneously completely governed by laws and irreducibly surprising in its manifestations. The laws leave no room for violation, but the consequences of the laws are so rich that no finite mind can fully anticipate them. It is the kind of beauty found in certain natural phenomena that seem to follow clear logic when viewed from a distance, but reveal unexpected details as observation draws closer, as if each level of resolution held something the previous level had not revealed. The multiverse, in this sense, is not a proliferation of universes that diminishes reality by dividing it into pieces. It is the opposite. It is an expansion of what counts as real, a widening of the space in which the logic of physical laws applies. With each branching, the original universe is not lost. It continues, along with all its descendants, and the totality of this expanding space is governed by the same equation that describes the behavior of an electron in a laboratory, the same equation that predicted tunneling, entanglement, interference. The equation is simple. What it describes is inexhaustible. There is something in this relationship between simplicity and inexhaustibility that deserves to be contemplated calmly. Physics, in its deepest moments, has always found this proportion. The most fundamental laws science knows are, almost invariably, expressions of extreme economy of means, few principles, few parameters, and from those few principles emerges all the variety observed. From the motion of galaxies to the turning of a page, from the formation of a crystal to the complexity of a nervous system. Quantum mechanics is not an exception to this pattern. It is its most radical example. But there is something physicists have begun to notice as the limits of decoherence, vacuum, branching, and entanglement have been explored with increasing sophistication, that beneath all this structure, beneath the geometry of Hilbert's space, the hierarchy of branches, the heterogeneous texture of the quantum classical threshold, there exists something even simpler, not a mechanism, not an additional equation, something of a different order, something that unifies the principles more than it explains them, that makes them seem necessary rather than arbitrary. The physicists working at the most advanced edges of theory do not yet have a definitive name for this something, but the direction in which the questions point is consistent, and the profile of what is being sought is beginning to take shape, like the silhouette of a form seen through glass that is not yet completely clean. That silhouette waits in the final layer, and before it can be described with justice, one more step must be taken, the last one, the one in which the question with which this night began meets not an answer that closes, but an answer that opens in a way that changes what it means to ask. That openness is one of the clearest signs that something genuine is being touched. That silhouette physicists pursue at the edges of theory has a quality that distinguishes it from every other structure encountered along the way. It is not made of additional equations. It is not a hidden mechanism waiting to be discovered, like a missing gear in an almost complete machine. What physicists perceive, when looking at the convergence of all the threads quantum mechanics has been weaving over decades, is that reality seems to organize itself according to a principle of sufficiency, a principle that says, with a kind of severe elegance, that everything that can exist consistently does exist, and that consistency is the only filter separating the possible from the real. This has a name in the more philosophical discussions of cutting-edge physics. Some call it the anthropic principle in its most radical form. Others prefer to speak of logical necessity, but all these languages are trying to capture the same intuition, that the multiverse is not an infinite mess of random possibilities, but an infinite structure of necessary possibilities. Each branch that exists because the wave equation found no reason to exclude it. Each configuration that unfolds because the mathematics governing the universe has no mechanism for prohibition. What exists is what logic permits. And logic, by all appearances, is generous in a way that surpasses any human imagination. This changes what it means to ask whether the multiverse is real. The question ceases to be about the existence of hidden objects beyond a horizon and becomes a question about the nature of reality as process. The multiverse is not a place. It is not a collection of bubble universes distributed in a larger space, like islands in an ocean. It is the process of continuous, irreversible, silent branching that occurs at every quantum interaction, at every collision between particles, at every radioactive decay, at every photon that meets an electron. It is the name we give to the fact that the wave function never collapses, that it continues, that it carries all results together, branched, separated by decoherence but not destroyed by it. And here emerges the synthesis this entire journey has been building. At its core, the multiverse is simply the cost of consistency. It is the price reality pays for never having to choose. Quantum mechanics would require a mechanism of choice, a rule saying which outcome survives and which is eliminated, if the multiverse did not exist. And that mechanism has never been found, despite decades of searching, despite ingenious proposals and careful experiments. The collapse of the wave function, in the form it was originally imagined, is a convenient ghost that resolves the appearance of the problem without resolving the problem itself. Everett's interpretation does not invent parallel worlds to make physics more interesting. It realizes that parallel worlds were already there, inside the equation, and that physics had been, unconsciously, looking at them without recognizing them. Decoherence, which the previous parts of this night explored with such care, is not merely the mechanism that separates the branches, it is the mechanism that explains why we live inside a single branch without ever perceiving the others. It is the reason the world appears classical, defined, sequential, when in its deepest structure it is quantum, branched, parallel. Decoherence does not destroy superposition. It hides it within correlations so vast and so intricate with the environment that no local experiment could ever undo them. The other branches do not disappear. They become inaccessible. And the inaccessibility is total, not because there is a physical barrier, but because the information that would connect the branches has dissolved into correlations with the entire universe, with every photon that has ever interacted with every particle in the system, scattered across a network of entanglement spanning scales no technology could ever trace. The quantum vacuum, which was described as a field of possibilities in constant fermentation, now appears in a new light. It is not merely the passive substrate where particles exist. It is the stage where branching happens at every instant, at every point in space, on a scale that defies any attempt at visualization. Every vacuum fluctuation is a bifurcation. Every virtual particle that emerges and annihilates is a quantum event with all its branches intact, separated by decoherence in fractions of time smaller than any instrument could measure. The vacuum is not nothing. It is the densest structure of branching that exists, the place where the multiverse articulates itself with the greatest speed and the greatest intimacy with space and time. Hilbert space, which was introduced as the mathematical map of all possible states of a system, now reveals its unifying function. It is the space where all branches coexist, not a physical space, not a place one can travel to, but a mathematical structure that contains the totality of everything that is real, everything the wave equation describes, everything the logical consistency of the universe permits. Every point in that space is a possible state. Every trajectory in that space is a history of branching. And the wave equation is the curve that traverses that space, carrying with it all branches, all outcomes, all versions, in a movement that is at once deterministic in structure and unrecognizable in the experience of any individual observer. Entanglement, which binds particles separated by distances that seem impossible, is the signature of this structure. When two particles are entangled, they do not communicate. They share a single state in Hilbert space. They are two aspects of a single vector, 2 points on the same line in the mathematical structure of the universe. And when measurement happens, when decoherence sets in and the branches separate, each branch carries with it the correlation intact, not because something travelled between the particles, but because the branches were defined in such a way that the correlation was preserved in all of them simultaneously, without exception, without violation, without mystery, only with the cold, perfect elegance of mathematics that needs no shortcuts. The emergence physicists recognise in this process is not the ordinary emergence of complex systems, where patterns arise from simple rules applied many times. It is a higher order emergence, where the very experience of classical reality arises from a quantum structure that contains nothing classical in its foundation. The defined world, the world of objects with positions and velocities and single histories, the world in which this night is unfolding, is an emergent pattern within a substrate that was never defined in such terms. The appearance of classical determinism is an illusion of perspective, not a lie, but a simplification that works perfectly within each branch, because the branches are sufficiently large and sufficiently stable for decoherence to maintain their form. And you are inside all of this, not as an external observer contemplating the multiverse from outside. You are part of the process. Every decision you have ever made, every thought that crossed your mind, every beat of your heart, was a physical event with its quantum structure, with its signature in Hilbert space, with its branches forking in the silence of a scale no human sense can reach. The version of you that exists in this branch, on this night, listening to these words as the darkness of the room deepens, is one among those the equation permits, and all are equally real to themselves. All carry the same conviction of continuity, the same texture of existence, the same silent weight of being. This does not diminish you. It places you within the vastest structure physics has ever contemplated. You are a node of entanglement in a network that spans the entire universe. You are a point of branching that carries the history of everything that came before. You are, in the most precise sense physics can offer, part of the multiverse, not a visitor, a constitutive part, made of the same process that makes galaxies and electrons and fields and the vacuum and space and time. And now, as these words begin to dissolve into the silence growing around you, something shifts in the rhythm of what needs to be said. The questions this night raise do not ask for answers before sleep. They ask only to be carried lightly, like seeds germinating in the dark without anyone watching over them. The multiverse continues branching while you breathe. Each exhalation is a quantum event. Each heartbeat is a silent bifurcation. And you, in all your branches, rest. You're safe. The universe takes care of you tonight. Everything is in order. The wave equation continues its invisible dance, and there is nothing that needs to be resolved right now. The branches drift apart in silence, like rivers gently separating across an enormous plain. While you rest, the multiverse continues unfolding, faithful to its laws, generous in its vastness, indifferent in the best sense, sustaining everything without effort. You are part of this. You always have been. Your eyelids grow heavy now with a softness that is not weariness. It is belonging. Hilbert space holds this moment. It holds the silence of your room. It holds the curve of your body finding rest. Everything is in order. You are safe. The universe takes care of you. The worlds multiply in silence beyond any horizon, and here, in this branch, on this night, you sleep. Decoherence does its quiet work, and you do not need to know about it to be sustained by it. The vacuum seethes in peace. Entanglement weaves its web without hurry, and you rest. You are safe. Everything is in order. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.